Hello, everyone. This is Jose with DuPont Medical Packaging Group, and welcome to our seminar here that we are doing today jointly with Spectrum Plastics. So just a few housekeeping things before we get started here, and to allow a little more time to let people to join in. So first, this presentation and the materials that you're about to hear and listen are copyrighted by DuPont Medical and Pharmaceutical Packaging as well as Spectrum. So the individual speakers are solely responsible for their content and opinions, and we're going to have the slides available for you tomorrow, where we'll send you a thank you email, and in that email you'll get copies of the presentation and also a survey. So we ask you to please fill out the survey, so that way we can hear from you, and please let us know how we did today. And then secondly, if you're experiencing any trouble in hearing the presentation or anything along those lines, just log out, disconnect everything, and then log back in. We found that that has solved most issues when you turn things off and turn them back on. So if you do experience any problems, just feel free to go ahead and do that and just jump back in. And then the last part also is that regarding questions. So there is a chat feature in the box there that you see that came up, and go ahead and write in questions. Now, if I can take the questions during the presentation, I'm going to go ahead and answer that. Michael will be one of our folks who's helping us behind the scenes here, and he may jump in and say, hey, Jose, we have a question here or there. So if you hear someone's voice, you'll know why. But we'll try to take questions. The questions that we do not take, we're going to get the answers to them and get them back to you. So we'll send that out in an email or in some other form, or maybe we'll have another seminar to just address the questions. And we'll try to leave a little time here at the end to also talk about this, all right? So with that housekeeping stuff off to the side, I'd actually right now like to welcome or bring on John Wolf from Spectrum Plastics. John, you want to say a few words to the group?
Sure. Thanks, Jose. I'm really pleased to be here. This is our first opportunity to get to present together since Spectrum Plastics had acquired the PeelMaster sterile packaging business. So this was a great kickoff, and it also gives me the chance to do something I never do. I did see your disclaimer, so this will be all on me, but I can offer everyone here a 100% guarantee that in this next hour and a half, you're going to learn some new things about Tyvek and sterile packaging, because I know that I have. So really looking forward to getting to share more about that and about Spectrum and our films division. So thanks again, Jose, for hosting and putting it together for us.
And John, thank you very much. And also I'd like to say welcome to the DuPont Tyvek family. You are the latest through the acquisition of PeelMaster, the latest member of the team. So welcome, and we look forward to working with you and hearing more about you here in the second half of this webinar.
You bet.
Okay, perfect. Thank you, John. So as you see there on your screen, you see the list of speakers. We're going to come back to these folks here a little bit later on. And so right now we're going to get into the Tyvek portion of this presentation. So some of you have seen a Tyvek 101 and some of you may not. So this will be a refresher for some of you, and for others it might be some new information. So we're hoping that you learned something today. So please feel free to ask questions if you need to. If I go too fast or something else, just let us know. So please feel free to contact us on at medicalpackaging.dupont.com. That is our website. So jump on there. We have a slew of information. Please also add us to LinkedIn and add me personally to LinkedIn. So send me an invitation, and I'll add you to that, so you can kind of stay connected with us and hear any new information that's coming at us. So let's get into the meat of the presentation and into this discussion, and let's talk a little bit about just a little bit of history in terms of how DuPont started. So back in the 1800s, Ben Franklin and Thomas Jefferson, they went to France and they went to the DuPont family and said, hey, come to the US and make some gunpowder for us. And the DuPont family said no. So then they said, well, we'll give you half the state of Delaware. And they said yes. They didn't really get the half the state of Delaware, but what they did is they got a lot of land, and they came over as land developers. But at the time, an individual could go out west and get 10 acres for free, so their land development thing didn't work out so well. So they had to make gunpowder. So DuPont made some of the best explosives anywhere in the world, and really that's how we started. And because of that, we have a culture of safety, and we also have a culture that's really based in science, and in a lot of engineers work at DuPont and run DuPont. And so we have a really long history. Now, we were in the explosives industry for a long time, up until the beginning of the 1900s. And what happened is that we got into some very basic polymer science and chemistry, actually, to set up experimental station in chemistry. And there was a guy by the name of Carruthers who invented nylon. And so that really changed the whole scope and kind of view of DuPont and where we would go. So we were the folks that started with nylon, and then from there we invented all kinds of other materials. So spandex, for example, lycra, and all these other materials. So all the yoga pants and everything you see out there, you have DuPont to thank for that. Now, a few years back, we sold that division to someone else, so they own the trade name of that and all of that, but that originally started with DuPont. And then as you can see in here, you can see that we had we also invented Teldar, Lycra, Kevlar, Nomex, and those materials in the 60s. Teldar is a film, so if you fly on a Boeing airplane and the actual wall that you touch, the film that you're actually touching, the surface is actually made by DuPont. And in some planes, we actually make the wall right behind it a honeycomb structure that's made out of Kevlar and Nomex. But we do a kind of bunch of really different things that you would not be aware of. Kevlar is used in anti-ballistic applications. Nomex is what the firemen wear, right? And Tyvek is what we're here to talk about. So we're going to talk a little bit more about that, and we'll kind of move on from here. Now, excuse me, now I'm going to switch gears a little bit, and we're going to talk about how Tyvek, which is a breathable material, right? How is it that a breathable material can still be a sterile barrier, right? And so we want to understand this concept. And in order to understand this concept, we kind of have to take a little step back in time, and we have to talk about a guy by the name of Louis Pasteur, okay? So Louis Pasteur, back in the 1800s, right? During that time, they didn't know about bacteria and viruses. They really didn't understand how people got sick. But Louis Pasteur, he postulated and he said, I think there's something in the air that was making people sick. And so he came up with this very clever experiment of trying to prove that. So he took a flask and he put a liquid inside of it, right? And inside of this liquid is some kind of nutrient, right? So just think of it like a chicken soup. Right? And then what he did is he put it in a very specific kind of flask that had a gooseneck design to it. So it had some bends and curves. And he boiled both of them. So in boiling both of them, you know that what you actually do is you kill off all the bacteria and viruses, right? And today, that process, we call it pasteurization after his last name. And so what we're doing is getting rid of that. And then the gooseneck provides a tortuous path. Now what happened is, what he did is he took one of the flasks and he cut the top off, right? And because he cut the top off, it was exposed to the air, so now the bacteria could make its way into the flask and contaminate it, hence it went bad. But the other side, the other flask that was still open to the air through the tube, but because of the twists and turns of the tube, the bacteria didn't make their way through. And so that stayed sterile. It stayed uncontaminated, right? Now this experiment actually happened in 1893. And you know, some of you have heard this presentation, right? So I'm going to ask the question, if this flask was still around today, would it still be sterile? So the question is, would it still be sterile? And the answer is yes. So if you go to the Pasteur Institute in Paris, France, you will see this flask. And so on screen right now, you're seeing a picture of the actual flask. Now, the end is capped because of evaporation. We don't want the liquid evaporating, and so it's capped now. But if it was still left open, there is nothing that would actually change the reason why that should become unsterile, unless you were to blow air into it. Those curves provide a tortuous path. a path that makes it very difficult for bacteria and viruses to make their way through, okay? So all breathable materials and their ability to keep bacteria out are based on this tortuous path. And not all tortuous paths are the same. There are different, abilities of different materials to be tortuous, okay? So we'll talk a little bit more about that. And so if you would, with the next slide there, Michael, please. So let's talk a little bit about the mechanism and how this works. There was a Dr. Talentire in England, and he did this study, and what he proposed, or what he actually proved, I should say, first he proposed and he proved, is that bacteria and viruses behave like particles. Actually, they mostly attach themselves to particles, but they behave like particles. So particles actually have no way of having any relative motion. They go with the flow of air, right? So they're always moving with the flow of air. So this is a really good close-up picture of some Tyvek filaments, and you can think of it this way. I can think of the air kind of blowing towards the screen or blowing towards the actual filaments. Now what happens is that those filaments, because in the case of Tyvek, it is high density polyethylene, we'll get into that later, excuse me. Well, that HDPE has a little bit of static charge to it. That static charge holds on to those particles when they hit the surface. Right? So as you can see there, you see particles going towards the screen, hits the surface. There's this one particle there that looks like it's on the edge, but if that were to fall off, it'll hit the next filament. And if it falls off that filament, it hits the next. The filaments of Tyvek, which are large and small, provide an incredibly tortuous path that it's very difficult for anything to make its way through to the other side. And when you add the electrostatic charge forces on there to hold it and hold those things in place, it's really a great sterile barrier. And we're going to talk a little bit about that through a very specific ASTM test. So there's an ASTM test called 2638. And what you're doing there is you have a machine, thank you, lots of words there, have a machine, and I'm going to put a sample in this machine, and then I'm going to seal it up. On the bottom, I'm going to have a particle counter. So I'm going to count how many particles go through. And on the top, I am going to inject 3 million 1 micron styrene spheres. Okay? 3 million 1 micron styrene spheres. And then I'm going to change the speed or the face velocity. And then I'm going to count on the other end how many particles made their way through. Okay? The screen that you're looking at right now and I should say the chart that you're looking at on screen shows the differences between that ingression. So on the bottom you can see is Tyvek and it's near zero, right? So you can see the purple and the blue line and the darker blue line, it's just near zero. It's I think 0.05% or 0.007 is the max p-value for Tyvek. It's really incredibly low. Those 1 micron styrene spheres had a really hard time making their way through. Now, as you go up the scale, though, you see 55-pound coated paper, 70-pound synthetic reinforced, and finally 40-pound coated paper, right? And so what's happening there is that depending on the fibers in paper, the sizes, it also will depend on the level of ingression that's occurring. So on the next slide here, what you're going to see is a picture comparison of Tyvek versus paper. You can see that there's a small and large filaments. Those are creating an incredibly tortuous path, but paper is very consistent in its fiber size. For example, if I went to the grocery store and I got a craft paper bag, right? So I have a craft paper bag. In order to make that bag strong enough for my groceries, they have to have very large fibers in there so it can have a great deal of strength. But when you have large fibers, what you also have, and then you can think of my fingers as fibers, you also have large gaps in between there. And those gaps are so big that craft paper is never used in medical packaging applications. Medical grade excuse me, paper, on the other hand, has smaller fibers, but they're still all consistent in terms of that fiber length and width. And so here you can see in this picture, you can see that there's gaps in between there, and it's in those gaps that those styrene spheres make their way through. Okay, so if we went back, and Michael, if you could just go back to the previous slide, you will see that this is what this is recording, that at very low velocity, right, we have some, some ingression, but then we're going to have a point where those styrene spheres will make their way through, and then the faster they're going, the more they're going to crash into something and stop. So let's think of that in a different way. If I'm on a motorcycle and I'm going through woods and all the trees are the same size and kind of distance apart, there's a certain speed where I can make my motorcycle and I can have the highest statistical probability of making it through to the other side. As I start to speed up and go faster and faster, I'm going to be crashing into a tree more often. So that's why it kind of peaks. I find that sweet spot, and then all of a sudden I'm going faster and faster, and it tails off, and then I'm going to be crashing into more trees. Tyvek, you can think of it as having not only big trees, but a bunch of small trees as well. The filaments that are larger and the filaments that are smaller combine in such a way to form a very complex pattern that motorcycle basically gets stopped very early on and does not make its way through. So are all breathable materials the same? No, they are not. Are all, because let me rephrase that, they are not, because the tortuous path is different, okay? Tortuous paths are different. Now, what's very applicable today is in the world of masks. So I'm just going to throw that out there so you can understand that a little bit. Tyvek, for example, is breathable, but not breathable enough to be used as a face mask. So the face mask materials, right, are actually going to have the fibers are going to be opened a lot more so that you can breathe in and out of them. But for example, N95 masks at 95%, what's going to happen is that they have an incredibly tortuous path for that bacteria to make its way through. If I was to use this shirt, because it's woven and it's cotton, it does not provide as much of a tortuous path. My coat here maybe provides a little more because I got a couple of layers in here, and if I breathe through this. So really, not only is it dependent on layers, but it's also dependent upon the complexity of those filaments that are used in those systems. Okay, so just a little side note for you, and we'll go on from there. So just to understand a little bit, Tyvek, it can be used in ETO sterilization, gamma, E-beam, steam, and sterad, right? Paper can be used in some, film can be used in some, right? There's different reasons for this, but really just to let you know that Tyvek is compatible across all those. With steam, you need to be careful to make sure that you stay under 127 degrees C. If you go above that in steam processes, the Tyvek will start to shrink. So that's kind of the upper limit from a steam sterilization cycle. So if you're running a 122 cycle, you should be good. If you're running a 132 cycle, it's not going to work for you. So, but more details on that, you can always give us a call if you need to understand that a little bit more. But one point that I want to make here on sterilization, and then we'll move on 1 second, is this. What is it that we are trying to do when we sterilize? And the answer is that we are trying to make the ability of that organism's, or we're trying to take away that organism's ability to replicate, okay? So we want to make sure that that organism cannot replicate. So we are going to leave it sterile. And so what we're after is destroying the RNA and DNA mainly. Okay, so if I destroy RNA and DNA, then that product or that bacteria virus can't replicate itself. For example, I can take some alcohol, right, and I can disinfect my hands. I can kill bacteria and viruses, but I don't necessarily destroy the RNA and DNA. And so these processes are very lethal, and these processes take it to another level of that destruction. That is what we need to do to make sure that we're sterile. Now, we can do a whole presentation on sterilization someday. My colleague Dan Floyd, he's the guru of sterilization, and someday we'll have him on here real soon to go ahead and do a sterilization seminar so you can understand all things sterilization. But just understand, if you're an MDM, that's what you're trying to do. Get rid of that organism's ability to replicate so that the product stays sterile, and go from there. So let's move on from that. And so let's talk a little bit about how Tyvek was discovered. So in a lab, there was a pipe going through the lab and the fitting developed a crack. And from that flowed out some polyethylene onto a lab table. A guy by the name of Jim White the next day came in and saw that and said, I think we can do something. That's where the idea came from. And so back in 1959, we made a small machine to be able to kind of prove this concept out. And then it took a bit of time before in 1967, we actually had our first commercial roll of Tyvek coming off of line 1 and 2 shortly thereafter. And so the first time, though, it was used in medical packaging was in 1972. So another question here for the group. Can anybody tell me what grade of Tyvek that was? And the answer is 1073B. So 1073B has been around since 1972. When they made that style, they did it perfectly. It was a perfect blend of thickness, of flexibility, of puncture, of tear, of breathability, everything. I mean, they just nailed it from day one. And so that's why 1073 continues to be our largest seller and continues to be our most popular style and continues to be the best Tyvek to use in medical packaging applications, right? And we'll talk about the other styles later on in this presentation. And so we have 2 locations where we make Tyvek, and that's in Richmond, Virginia and Luxembourg. And then we have various generations of those over the years. So generation 1, generation 2, and 3. I'm not going to spend a lot of time on this, but if you had anything to do with the MPTP or the transition protocol, you would have known what we needed to do to go from generation 1 to generation 2. But currently, all the styles of 1073B, 1059, and 2FS and 40L are made on lines 4, 5, or 7. They're not all made on all the lines. They're just, those are the 3 lines that are basically set up to do medical packaging. Okay, so here's a picture of the Luxembourg site, and you can see there in that round box is the location where the Tyvek line is, and then in the woods behind there, this is an older picture. The woods have been cleared out, and we're actually installing another line there. So we announced a couple of years ago or some time ago here that we are putting in a new Tyvek line, and so that's where it's actually being produced. And to give you an idea of scale, you can see the cars there on the side. Now this is the plant in Spruance, in our plant in Richmond, Virginia, and you can see that entire area over there on the left-hand side is where Tyvek is made. So these are not small facilities. Now, one of the questions I always get is, Jose, why does DuPont have a monopoly on Tyvek? And the reality is we do not have a monopoly on Tyvek. As most of you know, or maybe some of you do or don't, a patent lasts somewhere around 17 years. Now it's been extended a little bit for certain things, but let's say 17 years back in the day. So when was Tyvek discovered? In the 50s, right? When was it used for medical? In 72. So that patent has long expired. The thing is that no one has been able to actually make Tyvek, and so that's why we're the only ones that do. To give you an idea, when the machine is cold and someone hits the start button, one of the operators hits the start button, it takes 48 hours or 2 days before everything just stabilizes out and gets to the optimum condition so we can make medical grade Tyvek. I'm sure if you're an MDM and you told your boss it's going to take 2 days before I can make you first quality grade product, I'm sure they'd fire you. But at DuPont, that's not the case, and especially in Tyvek, because it's that hard to make. If the machine shuts down, it takes us about a week to start it up, and then every 3 to 4 months, we actually have to take the line down and for 2 weeks do a complete overhaul. Now, remember I talked to you about that startup? In starting up, the standard operating procedure, or the book to start it up, is 152 pages. So imagine going through 152 pages to start up a machine. And I tell you all this because I want all of you to understand that this process of making Tyvek is not easy. It's actually very complex. There is a lot of critical things that have to work and come together for us to be able to make Tyvek. But because of that, we have some and just an incredible material. So we'll go on from there. So in this little short video, where it's going to show you a little bit about the process that we actually make Tyvek, and what we're doing is we're taking the polyethylene film and we're putting it into solution. It's going to flow through a particular system, and then it's going to come out of a point where it's actually going to flash. And flash spinning is nothing more than like, it's just like a miniature, like just explosion, and it's going to actually generate small filaments and large filaments at the same time. And we're going to take those large filaments and small filaments that are just coming out, and we are going to direct them onto a moving belt. This picture that you're about to see coming up is some filament. So if, Michael, if you can just hold it there, you can see that it looks like cotton candy. It looks like a spider web. And what we're doing is there's a few layers that are in there, and we're doing one layer on top of another layer on top of another layer, and we're laying them down on a belt. So a belt is moving, and we're just laying layers on top of layers on top of layers. So we're building them up, and we're creating what's called a non-woven material. So this is not a woven material. My shirt is woven. This is a non-woven. It's just multiple layers of randomly distributed filaments that are going back and forth, and they're filaments because they're continuous. And we're going to just put all these layers together, and then we're going to bond it together and make what we know as Tyvek. So in this picture, what we're trying to show you is there's a finger there in the corner, and there's a filament, and somebody is actually pulling on the filament. And if we were to show you that, it would go back and forth across the screen. Why is this important? First, because they are continuous and because they are going back and forth, when I lock those in place, okay, what I am going to have is I'm going to have an incredible strength to them. The big filaments that are in there are what give me the strength. The small filaments are what actually give me the added microbial barrier. So the combination of the two is outstanding to be able to get large filaments and small filaments. Those large filaments also give me some great puncture resistance and tear resistance. And Michael, you can go ahead and hit the next one so the things come up on the side. And then what also I get is that I'm going back and forth. I bond it, and we're going to talk about bonding in a second, and we're going to fuse them together. That's what gives me a great machine direction and cross machine direction parity. So the properties that I'm getting in this orientation and this orientation are fairly comparable because of this back and forth, and then I'm locking it into it. Now it also gives me really good thermal stability in the sense that I can heat seal this and it's not going to shrink. It's just going to stay right there. And so it's got very good properties for heat sealing and those kinds of things, right? Because it's also a continuous filament, it's also very low particle generating, right? Very, very low particle generating. And then finally, because these are randomly distributed filaments, what happens is that in some areas you get some thicker, and I mean thicker, like wider filaments in other areas. So a lot of times people go like this. They like kind of look at Tyvek and they like look up at the light and go, see, Jose, there's a quality problem here. That thick side's in there, and it's not a quality issue. It's just that those filaments are thicker than other ones. On rare occasions, you might have some that are just a little bit, too much, but that's super rare. But for the most part, what happens is that's just a normal variation of the distribution of the filaments in our process. Okay, so we take this material that we've spun, and we're going to bond it together. So we're going to put the skin on it, as you know and love and you feel every day. And that's called the bonding process. Now there's two different types of bonding processes we use. One type of bonding process is called the hard structure bonding process, right? So go ahead, Michael. And this bonding structure goes through this very specific way, and we're going to go into detail. And that's how we make medical and graphics and building and tags and labels, all these different styles that we have that are hard structure. Okay, we go through a second or a completely different bonding process when we are making soft structures. So we're using point bonding. So now these things are going to be bonded at points so that the material is much more flexible or cloth-like. So soft structure is completely different. Right now DuPont is very proud to be at the forefront of this whole COVID defensive system, in the sense that we make the Tyvek bunny suits, right, that you've seen lots of people use. It's really the #1 suit for protection, and we are making as many of those as we can to help fight the battle out there and protect our frontline workers. But it runs through this very specific process, and we're really proud of all the work that's being done by that division and all the things that we do with them. But let's now go back and talk a little bit more in terms of detail of bonding for hard structure. So in this particular graphic, you can see that round cylinder is heated. It's a big drum, and the surface of that drum is so smooth and just so smooth that it's shiny and it's mirror-like. It's an absolute, if you looked at it, it'd be like looking at a mirrored surface. What happens is that the Tyvek that's unbound comes against that, touches that drum, that side gets heated, and the filaments stick together, right? So they get stuck together. And then immediately after that, we cool that one side, and then we flip it to the other side, and then we bond the other side, and then we cool it. And that's how we form Tyvek that has a skin, and we say it has a skin, a core, and a skin. Okay. During the bonding process, we're doing several things. First, we're stabilizing the surface so you can use it, right? You can seal to it, you can coat to it, you can print on it, right? But the other thing also is we're trying to make sure that we keep the breathability that you need for medical packaging, and we are shooting for 22 to 23 Gurley Hill seconds on the breathability side of things. So we've got to make sure that it's breathable. So if we put too much pressure, it becomes less breathable, not enough. It's not going to be to that spec, right? And then also this can affect surface variability. So let me explain that in the next slide. So as you can see in this picture of Tyvek here, what you're seeing is this thin side there where the 001, and if you look right above that, you see how that's thinner than over here in the KV side and how that's a little bit thicker. What happens is if I was to give you a super flat Tyvek, and the flattest Tyvek I can give you is probably going to be our graphics grade. So if you ever see me and I give you one of my business cards, this thing is super flat, it's wonderful. But what I've done here is I have compressed it so much, and I have kind of joined all the filaments so much that this has a Gurley Hill seconds reading of about 75 to 80. That's unacceptable for medical packaging. You need much more breathability. So for me to make it flatter for you, I would have to take away the breathability, okay? So that's why Tyvek medical grade has normal surface variations, as we call them, right? It actually varies in thickness. It's just part of the process. Another way to think about it is if you see the inset picture, that second picture, you can see right there where the 07 is, or you can see it right above where if the filaments are quite high and just next to it are quite low. So if I was to measure right there in the high spot and just move just a fraction lower, I'm lower, and I would measure a different number. There's nothing wrong with this. This isn't we've been making this since 1972. There's always going to be that variability. It's just most folks have not understood the process of making it with this cotton candy or spider web, and we're building it up that there's going to be natural surface variations. And we can't take all of those out because then we would just eliminate the breathability of the material. Always going to be some surface variability, but we're good. We take master rolls that are 10 feet long and we shrink them down, or cut them down to smaller sizes, and then your SPMs will take those and convert those and make the products that you use and love every day. Okay, so let's talk a little bit now about the specific details of what Tyvek is. So Tyvek is 100% high density polyethylene. It is also, the polyethylene that we use is FDA approved for food contact polyethylene. So that means it's very clean and pure. And we want it to be clean and pure because guess what? This can touch a medical device. And so because it can touch a medical device, we want to make sure that we use the cleanest and purest resin. So we don't use any reclaim, regrind, recycled, nothing. It's pure virgin polymer that we're using in this process to go through. Sorry, excuse me. So because it's so clean and pure, guess what? It is great recycled material. The material is going to give you some of the best. It's going to be incredibly pure. Sometimes some recyclers have trouble chopping up Tyvek. And so because they have trouble chopping up Tyvek, they say, we can't recycle it. It isn't because they can't, it's because the mechanical chopping up process isn't easy for them. There's other people who have figured it out, but Tyvek is 100% recyclable. It can go into a whole slew of applications that are, HDPE in terms of what you need to come out of the other end. Now, a couple of things we don't do, a few things we don't do. We don't corona treat. And corona treatment is when I take an electrical arc and I pass it over the surface of a film, or in this particular case, Tyvek. When I am passing an electrical arc over any plastic, what I am doing is I am actually ripping that hydrogen off. When you saw that diagram before of the molecules, right? I am ripping hydrogen off and I am leaving it negatively charged. When I negatively charge something, I am ionizing the surface. Inks bond ionically. The surface is now ionized, and boom, I'm going to get some great adhesion. And so our graphics grade, you can see like 6-color press runs. You can see these beautiful, you can put a picture or print a picture on graphics grade Tyvek, right? But here's the deal. With medical grade, that little spark, right? And by the way, this is a plasma treater right here, as opposed to a corona treater that you're seeing in the picture. But I love this picture so much, but it tells the same story. You can look at that little, like that glowing area as like a lightning bolt, and if my discharge is too big, I can actually induce a pinhole and drive a pinhole into the Tyvek. And so for medical grade, we do not corona treat, which means print is going to be much simpler. It's going to be 1 color, 2 colors, maybe 3. You're going to have a little drying time and some other stuff. So if you run into any processing issues with printing of Tyvek, just let us know and we'll be able to assist you on that. But we don't corona treat. We don't want pinholes in it. We also don't put a UV additive in there. So the frequency of ultraviolet light is such that it can actually break down the polymer and actually fracture it, in HDP and Tyvek especially. So if you were to take a piece of Tyvek that's medical grade and you leave this out in the sun for a month, it will actually start turning to powder. It will actually just fall apart because that UV is actually inhibiting it. Now, we don't put a UV inhibitor in here because, again, it's an additive and it can come out and contaminate a medical device. So we don't do it. We also don't expect that you're going to leave your medical device out in the sun, and we just don't think that's going to happen. So no problems here, but we just want to let you know that we do this so that, in case you have long-term exposure of UV light. Most of the applications, we've had lots of questions, do not come under, aren't enough UV light to actually degrade Tyvek. But if you were to leave it in the sun, it will fall apart and actually just disintegrate into powder. The last thing that we don't do is we don't add an anti-stat treatment. And an anti-stat is nothing more than a surfactant or a soap. And soap is the coolest molecule out there. Now, you may think I'm a geek saying that. I was a chemistry major in college, so, I'm a bit of a geek. But it is the coolest molecule out there. And you know why? Because soap is one of the only few molecules that can, at one end, will bond covalently, and at the other end will bond ionically. And that's a big deal. Okay, so one end bonds ionically, one end bonds covalently. So what does that mean? So when I take a shower and I sit there and I'm soaping up, well, one end of the soap molecule is actually attaching itself to the organics and oils. And then when I rinse off, the other end will attach itself to the water, and off it goes. Right? So that's why when you put soap in a greasy pan, it actually dissipates because one end is bonding to the water, one end is bonding to the oil. Okay? Now, on a humid day, when you have a humid day, you can't take the balloon and rub it against your hair and put it up on the wall. It just doesn't work. On a dry day, when there's less humidity, you can do the balloon trick and the static generates because it's drier. So the theory behind an anti-stat is this. I put a surfactant or a soap on the surface of my film or whatever it is, and I'm going to draw, moisture out of the air, and this moisture is going to come to the surface. Now I have a higher level of moisture on the surface of this material, and because such, I'm going to minimize the level of static charges I can develop. And so what I'm doing is increasing humidity levels, and so thereby minimizing and static charges. So that's how an anti-stat works, right? And we don't put it in medical grade Tyvek. Why? Because it's an additive, a soap or surfactant. It can come off, it can contaminate a medical device. So what does this mean for you? A couple of things. What it can mean for you is that sometimes we have customers complain and saying that Tyvek's dirty, and it's not that the Tyvek's dirty. Sometimes the statics can bring in the dirt from the air and attach it on there. And also if you have automated systems, you have to have enough humidity or static control so that when you do a pick and place with lids, that they will pick and place and not stick together because of the static. Okay, but if you have any issues on that, again, contact us. We'll help you out with that. So in the recap, right, high density polyethylene, FDA approved for food contact, no corona, no anti-stat. We flash spin it, and then we bond it together under heat and pressure to put the skin on it, right? It's continuous filaments, helping, which is one of the main reasons it's so clean and strong, right? And they're randomly distributed, non-directional. So now I've got really good machine and cross-machine direction strength, right? So that's kind of Tyvek in a nutshell. Now, if you see here, these are our 4 grades of Tyvek. Like I said, 73B was produced way back in 1972. Many years later, folks asked us, they said, well, we don't need something as strong, so we came up with 1059. The way that we make 1059 is we speed up the belt just a little bit, and we make 1059. If we want to make 1073B, we slow down the belt, and we're making 1073B. So it's not, there's no other difference in the process other than that to make 1059 or 1073. 2FS is different. You put titanium dioxide in there. It's a whitening agent. It makes it look brighter and whiter, completely different. And then our newest material is 40L. So 40L is a very, very lightweight material that's used in competitive situations with paper. It is stronger than paper because it's Tyvek. You have a lot of, bunch of different advantages from moisture resistance, breathability, all kinds of different things that are designed into 40L. So if you have some specific paper products where you're looking for replacement because you may be having some issues, 40L is the right product for you. So this is our current lineup of all the medical grade Tyveks that we have. And so with that, we are here to support you and to help you. So if you have any issues with Tyvek or running it on your lines or on-site technical or anything else, and we have all kinds of extensive data that you need to use for your PMA submissions or for 10K or for 10K submissions, just let us know. And also lots on the 11607, and we've had a seminar on 11607, and we can have another one of those as well sometime here in the near future. So just let us know what, also in your feedback to us, please let us know what other seminars you'd like us to hold for you in general. So anyway, that's kind of it on Tyvek. I know I kind of flew through that. I might have flown through it a little quicker than usual, and then a lot of information to kind of go at you at once, right? But we want to make sure to kind of get through this. And again, we can answer more in the questions at the end, or just actually submit some questions, and we'll get those answered for you as soon as possible. So now I'd like to I'd like to bring John back. John, are you there? There you are, sir. So I'm glad you were, how was that?
Jose, that was outstanding. And you now caused me to break one of the cardinal rules of presenting, which is never try to follow such a good presenter because you raised the bar so much on the rest of us. But that was excellent. Thank you for that.
Well, thank you, and we're glad to have you. And so during this half of the presentation, our folks at Spectrum are going to present some great information for you. And so I'll let John right now take over. And so John, all yours.
Thanks, Jose. So hello, everyone. It's me again. Really pleased to get to take you through a bit more about Spectrum Plastics Group, our films division in particular, and then we'll talk through some options and information around Tyvek converting. So I will lead off with that outline. I have the privilege to lead the films division for Spectrum. Been in packaging for 25 years, and I learned so many things in that Tyvek presentation that it'll take me a while to process it all. I'll be joined later by Chris Brewster, our engineering manager, and Ben Stevens, our project and process engineer, both who are based in our Wisconsin facility. So let's jump into a little bit about Spectrum. So Spectrum is a leader in the development and scaled manufacturing of critical polymer-based components for the medical market. We do this through 4 operating divisions. So we have a tubing and assembly division. We have a specialty plastics and injection molding business, a packaging division, which is the films that I lead, and then in a vascular and assembled devices division. We do this through 18 plants around the globe with over 2,000 employees, and our comprehensive product and capability portfolio look to make us a first call solutions provider for the demanding global medical device market. So let's dive in a little bit more about films. Unlike DuPont, we weren't granted half a state to get started, but we did start well over 70 years ago in the Chicago area, focused on blown film extrusion and converting. While we were initially focused on the food and industrial end markets, we entered the medical space in 1990. And since then, our medical flexible packaging has grown significantly to have a wide range of solutions for both the sterile and non-sterile applications. In late 2020, our division closed on the acquisition of the Peelmaster medical packaging business based in Niles, Illinois, which is about 40 miles from our Pleasant Prairie, Wisconsin facility. And by doing that, we felt very strongly how it advanced our goal to be a custom, scalable solution provider for the medical device market. Notably, with this acquisition, as Jose mentioned earlier, we were awarded authorized converter status from DuPont for sterile medical packaging. So we're really pleased how this has expanded both our reach in the market and then what else we can offer to customers. So diving in just a little further about who we are and where we are. So our headquarters and largest location is in Pleasant Prairie, Wisconsin. We have 33 blown film lines there with multiple converting lines that can do both sterile and non-sterile packaging. We do printing in line and out of line up to 4 colors. Our second location is in Costa Rica, where we also do blown film converting and tubing extrusion. There we have 5 blown film lines, 6 medical tubing lines, and 5 converting lines that can do sterile and non-sterile packaging. And then we get to introduce the newest member of our family, the Niles location. There we have 4 sterile pouch lines, a header bag line, die cut lids production, and over 800 tools for Tyvek sterile packaging. So we feel very positive about what we're able to do. This business has continued to grow and become an even larger part of our portfolio. So with that, I'm going to turn it over to Chris Brewster, and he will start to take you into some of our capabilities and the things that we do. Go ahead, Chris.
Thanks, John. Our relationship with DuPont Tyvek allows the Spectrum Plastics Group to provide innovative custom solutions for the medical markets. In doing so, they provide products to help reduce physical damage, as well as provide a microbial barrier, as Jose had spoke about, to ensure product sterility. Our engineering team fields many requests for converted sterile packaging. We respond to these requests with Tyvek solutions coupled with Spectrum Plastics Group's film innovations. So what do end use factors need to be considered when designing a Tyvek sterile package? I think first of all is manufacturability. Is your package configuration optimized for manufacturing on your shop floor? Next would be integrity. Will the package maintain a sterile barrier through manufacturing and the supply chain? But also, what are the performance criteria that need to be met for the end use? Additionally, appearance. Does the package clearly illustrate its contents and information for use? And then finally, is it easy to use? Will the clinician be able to open the package aseptically? On the next slide, we will begin to provide an overview of the tools we use to design. DuPont provides a product slate that allows Spectrum Plastics Group to integrate our custom film solutions for converting sterile packaging. Now Ben is going to introduce a few of these topics further, including peelable pouches, header bags, square and die cut lids, as well as form fill seal solutions with DuPont Tyvek. Ben?
Hi, Chris. Thanks. And hello to everybody. Thanks for joining our webinar today. I was asked, as Chris mentioned, to discuss a few different options that we can offer here at Spectrum Plastics for converted medical packaging. I'm going to start off talking about Tyvek peel pouches. What is a Tyvek peel pouch? Generally, this is a combination of webs designed for use with a light item where seeing the contents of the pouch is critical. Obviously, one of the main characteristics and design features for a pouch is to maintain sterility for the lifetime of the product. But while in design phase, I want us all to make sure that we keep in mind that during the lifetime of this product, packaging product, it's going to see shipping and warehousing time. So we have to consider those items when designing. 3, we have to consider size of the product that's going into the pouch. We don't want to design a pouch that is so much bigger than the product that's going in it that the contents of the pouch can move around and cause unnecessary abrasion or pressure on the seal areas. We also don't want to have the pouch so small that after the pouch is filled with its contents, that the contents are pushing out on the seal area. That could severely affect the integrity of the pouches. At Spectrum, we generally design our peel pouches with an opening force of 1 to 2 pounds peel force. I do want to mention that during the design phase, we want to make sure that we are hitting the right peel strength for the application. Obviously, if we're packaging a swab versus a tubing set, there may be a different peel value necessary. Some of the materials that we can offer from Spectrum are a PET PE, a nylon PE, and a polypropylene PE combination. We also offer a customizable polyethylene-based proprietary film that's produced right here in Pleasant Prairie, Wisconsin. That can be offered in gauges from 4 to 10 mil. All of these films can be used in combination depending on the specification with coated or uncoated Tyvek 40L, 2FS, 1059B, and 1073B. Some attributes for you to consider. Our maximum length by width is 28 by 28 inches. Minimum 2 inches by 4 inches. Our pouches can be printed or unprinted up to 4 color. Our team can help your team develop your pouch, whether you're going to be utilizing a hand-loaded or an automated packaging system. All of our pouches have a nice clean peel with no fiber tear, great for aseptic presentation. All of our pouches are compatible with most of the major sterilization methods. Next, going to talk a little bit about header bags. What is a header bag? Generally, header bags are going to be used for larger, bulkier devices, such as trays, kits, tubing sets, maybe procedural sets. Again, sizing is critical with these. We're going to use the same thought process as we did for pouches. We don't want the header bag to be too big or too small. Again, the opening feature that we designed for the peel force, we're looking at, again, 1 to 2 pound peel force, but Spectrum can provide you a custom solution if necessary. Materials that we use for the body film, we use a proprietary blend of polyethylene-based material. It's made right here in Pleasant Prairie, Wisconsin. This is nice because it offers both our Wisconsin and Niles facility a custom-based solution for our header bag films. Spectrum also has a proprietary peelable layer. I mention this because what's nice about this is the peelable layer, again, is made here in Wisconsin. We can vary peel forces if necessary. What it does is it creates a permanent bond to the Tyvek. We can see this. One side is permanent. The next side, as we peel open, offers a nice clean peel reveal at that 1 to 2 pound opening force. These films are completely capable with both uncoated and coated 40L, 2FS, 1059B, and 1073B Tyveks. Some other key attributes: 52 inches wide by 40-inch length is the maximum size, and they go down from there. Film gauge range generally from 3 to 6 mil. Custom solutions are available. Can be offered as non-printed or printed up to 4 colors, and all, of course, will have a nice clean peel for aseptic presentation. I do want to mention that we are working on using a header bag design in combination with a linear tear film as an alternative opening feature. Moving on to Tyvek square and die-cut lids. What are these? These are essentially pieces of Tyvek that are cut to size to fit a preformed container. Generally, we utilize a coated 1073 and 1059 Tyvek, but depending on requirements, we might be able to use other products. What's the difference between a die cut and a square cut lid? A die cut lid is something that is actually matches the shape perfectly or near perfectly of the preformed container. Square cut lid is, as the name implies, a square piece of Tyvek with 90-degree corners on each of the four corners. I mentioned the difference because as we're going through, a square cut lid may offer a better cost point, and also as a design feature, a square cut lid with a rounded corner may actually present you or your end use customer with an opening feature for that container. Again, these can be printed up to 4 colors. Mention the sizes. For square cut, maximum width is about 24 inches. Minimum width is about 2 inches. Length of these is essentially unlimited. For our die cut options, we can offer up 13 by 21 inches maximum and a minimum of 1.5 to 2 inches. Finally, I'd like to talk a little bit about our form fill seal solutions. Spectrum has developed a proprietary polyethylene-based film that's met many demanding applications. It's got excellent puncture strength, abrasion and crack resistance, and it offers people a very wide processing window. Another design consideration, as form fill seal solutions are now creating more of a 3D type package, we have to consider drawdown, basically how deep you're forming this packaging solution. I mentioned this sometimes directly correlates to the gauge of the film. Same thought process again for how big or how small. We don't want any of the contents of the pouch or the form fill seal solution to create any damage to the packaging. Again, we have a proprietary polyethylene-based solution produced in Pleasant Prairie, Wisconsin. Gauge range generally of 3 to 16 mil. These films can be offered as clear, tinted, opaque, whatever your solution requires. Again, this film has excellent forming qualities, great clarity, excellent puncture resistance. Many times we've been able to take and reduce the gauge of an incumbent film for some of our customers. Many times our tensile strengths are comparable to that of nylon. Also, our films offer excellent cornering thickness. I mentioned this is an inherent weak area in this type of packaging, so the thicker you can maintain the film in the corners, the better. As the slide says, our cornering thickness is generally above 1 mil. I also wanted to mention that we're working with multiple form fill seal machine OEMs to develop future bottom web options, which would include a direct seal to uncoated Tyvek. So stay tuned for that. That's all I have for you today. Thank you again for joining. I'm going to hand this back over to John and Jose to wrap up. Thank you.
We're going to bring this to a close. I know there's a few questions that we haven't had a chance to kind of address, but we're going to promise you, whoever asked us, we're going to email you directly. We're going to get back to you into some of these, right, and address some of these questions. And so, again, if you have any questions, here's the contact information for us. We'll be sending the presentations from, the Spectrum group, and in there will be all their contact information as well. So ask us anything you like, and we're here to help you. And so any words from you before I completely close the seminar today?
No, Jose, really just to say thank you again to you and the Medical Tyvek team for hosting the webinar. Really pleased for this to be a part of our Spectrum Connect week. And I think, this is a nice centerpiece. I was pleased to be a part of it. And thanks, Chris and Ben, for your work.
Thank you.
Perfect. And on behalf of DuPont, I'd like to welcome the Spectrum family again to our family, the DuPont Tyvek family. It's a fun family. It's a good group of people, and it's a fun industry to be in, and so welcome to this side of it. And to all of you online, thank you for taking the time out for today's seminar and webinar. And again, we'll address your questions. We'll get stuff back to you. And if you have any further questions, just feel free to get back to us. And so thank you, and have a wonderful day or night wherever you may be. So thank you.